Look up tonight. Between every star you see, there is darkness. That darkness seems ordinary, the natural backdrop to a glittering sky. But it should not be there. If the universe is filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, then every direction you look should eventually land on a star. The entire sky should blaze with light. It does not. For centuries, this simple observation broke the laws of physics. Scientists called it a paradox, and when they finally solved it, the answer revealed something far worse than emptiness. The darkness is not a void, it is a message. And what it tells us about the nature of the universe, its age, its limits, and what lies forever beyond our reach, is terrifying. If you find these kinds of deep explorations of the cosmos fascinating, consider hitting that like button and subscribing. Now, settle in, get yourself comfortable, let's begin. When astronauts leave Earth's atmosphere and look out from the International Space Station, they see something that should feel familiar, but instead feels deeply wrong. The sun hangs in the void, blazing with the same ferocity it shows from the ground. But the sky surrounding it is black. Not deep blue, not the purple of twilight. Black. Absolute, total, uninterrupted black. On Earth, we take the blue sky for granted. Sunlight enters the atmosphere and collides with nitrogen and oxygen molecules, scattering shorter blue wavelengths in every direction. This scattering is what paints the sky blue during the day, and creates the orange and red gradients of sunset as light passes through thicker layers of air at low angles. Remove the atmosphere entirely, and the scattering stops. The sky becomes whatever colour the universe actually is, and the universe, apparently, is black. Most people hear this explanation and feel satisfied. Space is dark because there is no air to scatter light. Case closed. But that answer is dangerously incomplete. It explains why the sky around the sun is not blue in space. It does not explain why the sky around the sun is not white with starlight, and those are two entirely different questions. Confusing them has hidden one of the most unsettling truths in all of science for centuries, and most people alive today still do not realize it. Here is the problem. Our galaxy alone contains between 100 billion and 400 billion stars. The observable universe holds an estimated 2 trillion galaxies, each one packed with its own billions of stellar furnaces. When you add it all up, the cosmos contains roughly 200 billion trillion stars. Many of them burn far brighter than our sun. That is not a typo. 200 billion trillion individual nuclear reactions blazing in every direction across the full volume of space. With that many light sources filling the cosmos, the night sky should not be dark. It should be blinding, not just bright, not just glowing. Every patch of sky, in every direction, at every hour, should burn with the radiance of a stellar surface. The entire dome above your head should look the way the disk of the sun looks at noon. Wall-to-wall brilliance with no dark gaps anywhere. It does not. The night sky is mostly black. Between the scattered points of starlight, there is darkness. Deep, cold, ancient darkness that has been there every time a human being has looked up since the species began. And for most of human history, nobody thought twice about it. The darkness seemed natural, expected, obvious. But it is not obvious. It is in fact one of the most profound contradictions in the history of physics, and it took centuries of effort by some of the most brilliant minds in science to understand why. The argument is simple enough that anyone can follow it. Imagine the universe is infinite in every direction, not just large but truly infinite, stretching outward forever, without boundary or edge. Now imagine that this infinite universe is also eternal. It has always existed. There was no beginning, no moment of creation, no first second. Stars have been burning for all of time. Finally, imagine that this infinite eternal universe is roughly uniform. Stars are spread through it more or less evenly, not clumped exclusively in one corner but scattered in every direction at every distance. These three assumptions, infinite, eternal, and uniform, were the default model of the cosmos for centuries. Philosophers and astronomers treated them as self-evident. The universe simply was. It had always been. It would always be. And it was the same everywhere you looked. But if you accept those three assumptions, something catastrophic happens to the night sky. Pick any direction. Look along that line of sight outward into space. If the universe is infinite and filled with stars, your line of sight must eventually land on the surface of a star. Maybe the nearest star along that line is 10 light years away. Maybe it is 1,000,000. Maybe it is 1,000,000,000. But in an infinite universe, there will always be a star somewhere along that path. No matter which direction you choose, the result is the same. Every single sight line terminates on a stellar surface. There are no gaps. There are no empty patches. Every point in the sky should be occupied by the face of a distant star. Now consider what this means for brightness. A single star at great distance appears faint, certainly. The inverse square law guarantees that. Double the distance, and the star appears 4 times dimmer. Triple the distance, and it appears 9 times dimmer. This seems like it should solve the problem. Maybe distant stars are simply too faint to contribute meaningful light. But the mathematics betray that hope immediately. Imagine space divided into concentric shells centered on Earth. The first shell extends from 0 to 100 light years. The next extends from 100 to 200 light years. The third from 200 to 300. And so on, outward forever. Each shell is thicker than the last in terms of volume. As you move to larger and larger shells, the volume of each shell increases with the square of the distance. This means each successive shell contains more stars than the one before it. The stars in the more distant shells are individually fainter, yes, but there are proportionally more of them in each shell. When you do the calculation, the increasing number of stars in each shell exactly compensates for their decreasing individual brightness. Every shell contributes the same total amount of light to the sky, and in an infinite universe, there are infinitely many shells. The result is inescapable. The total brightness of the sky, summed over all shells extending to infinity, should be infinite. Or, more precisely, every point in the sky should glow with the average surface brightness of a star. The entire sky should look like the surface of the sun. Day and night should be meaningless concepts. You would not be able to distinguish the disk of the sun from the background sky because the background itself would burn at the same temperature. The earth would be sterilized. Life would be impossible. The universe would be a furnace of light with no shadow anywhere. That is what the math demands. And the math is not wrong. The logic is airtight given the assumptions, which means the assumptions must be wrong. Something about the idea of an infinite, eternal, static universe filled uniformly with stars is fatally flawed. The darkness of the night sky proves it. This problem has a name. It is called Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers, who described it in a publication in 1823. But Olbers was not the first person to notice the contradiction. The problem stretches back far earlier, and its history reveals how long humanity struggled to understand what the darkness was trying to tell us. The first person known to have raised the question was an Englishman named Thomas Digges. In 1576, Digges proposed a model of the cosmos in which stars were scattered throughout infinite space rather than attached to a single celestial sphere. He immediately confronted the problem. If stars extended outward forever, why was the sky dark between them? Digges never solved the puzzle. He simply assumed the distant stars were too faint to see, which, as the shell argument demonstrates, does not hold up under mathematical scrutiny. In 1610, Johannes Kepler revisited the question and reached a startling conclusion. The sky is dark, Kepler argued, because the universe is not infinite. The darkness between the stars is evidence that space has a boundary. Beyond that boundary, there are no more stars and no more light. The dark gaps in the sky are simply the regions where your line of sight passes through all the stars and exits into the void beyond the edge of creation. Kepler essentially used the darkness of the night sky as proof that the cosmos was finite. It was an extraordinary leap of reasoning for the early 17th century, and while his specific model of a bounded cosmos was wrong in its details, his instinct that the darkness carried physical information turned out to be one of the most important insights in the history of astronomy. Over the following 2 centuries, other scientists took their turns wrestling with the paradox. Edmund Halley addressed it. In 1720, the Swiss astronomer Jean-Philippe de Chazeau explored it in 1744. providing some of the first rigorous mathematical treatments of how starlight should accumulate in an infinite universe. But it was Olbers in 1823 who gave the paradox its widest audience and whose name became permanently attached to it. Olbers proposed a specific solution. He suggested that interstellar dust and gas absorb light from distant stars, preventing it from reaching Earth. The universe might be infinite and bright, but we cannot see most of the brightness because cosmic dust intercepts it before it arrives. This sounds reasonable. Interstellar dust does exist. It fills the space between stars in vast clouds and thin hazes. It dims the light from distant objects. It reddens starlight by scattering shorter wavelengths more effectively than longer ones. Dust is real and its effects are measurable, but Olbers' solution contains a fatal flaw that was not immediately recognized. The flaw is thermodynamics. When dust absorbs starlight, it does not destroy the energy. It absorbs it and heats up. The warmer the dust gets, the more radiation it emits on its own. Given enough time, the dust reaches thermal equilibrium with the radiation field surrounding it. At that point, the dust itself glows just as brightly as the stars whose light it was blocking. The dust becomes a secondary source of radiation, re-emitting every photon it absorbed. In an eternal universe where this process has been running forever, the dust would have long since reached equilibrium. It would contribute its own brightness to the sky, rather than removing brightness from it. The darkness returns. Dust postpones the paradox. It does not resolve it. This is a critical point because it eliminates one of the most intuitive escape routes. People often assume that matter between the stars could act as a shield, absorbing distant light and preserving the darkness. But energy cannot be destroyed. It can only be converted and re-emitted. In an infinite, eternal universe, there is nowhere for the energy to go. Every absorber eventually becomes an emitter. Every shield eventually becomes a lamp. The darkness cannot be maintained by obstacles alone. Another common suggestion is that distant stars are simply too far away for their light to matter. We addressed the mathematics of this already with the shell argument, but it is worth emphasizing just how thoroughly this idea fails. People underestimate the power of infinity. Yes, a single star at a distance of 1 billion light-years is extraordinarily faint, but the number of stars at that distance is extraordinarily large, and at 2 billion light-years the number is even larger. At 3 billion, larger still. Infinity means there is no distance at which the total contribution from all stars at that distance drops to zero. Every shell adds the same net brightness. There is no threshold beyond which the light simply fades away. In an infinite cosmos, the contribution from distant stars is bottomless. No amount of distance saves you. A more sophisticated objection involves the finite lifetime of stars. Stars do not burn forever. They ignite, they fuse hydrogen and heavier elements in their cores, and eventually they exhaust their fuel. Massive stars live only a few million years. Even stable stars like our Sun will last only about 10 billion years before expanding into a red giant and fading into a white dwarf. If stars die, then perhaps the universe is not uniformly bright because at any given moment, many former stars have gone dark. They no longer contribute light to the sky. This objection is closer to the truth than the others, but it still does not fully resolve the paradox under the original assumptions. In an eternal universe, dead stars are replaced by new stars. Star formation is an ongoing process fueled by the gravitational collapse of gas clouds. As long as gas exists, new stars will form to replace the ones that have died. In an eternal universe, this cycle has been running forever. The average stellar population at any given time should be roughly constant. The dead stars are replaced, the light continues, and the sky should remain bright. But this objection does point towards something important. It suggests that time matters. The duration of stellar burning, the lifespan of individual stars, the history of star formation, all of these temporal factors influence how bright the sky should be. And this is the first hint that the paradox might be resolved not by changing the spatial assumptions about the universe, but by changing the temporal ones. Not by limiting how far the universe extends, but by limiting how long it has existed. Here is where the intellectual history becomes remarkable. For centuries, scientists treated the darkness of the night sky as a minor curiosity, a puzzle to be filed away alongside other unexplained observations. They proposed solutions. dust absorption, stellar rarity, finite universe boundaries. Each solution was tested and found wanting, but no one took the next step. No one followed the logic of the paradox to its radical conclusion. The darkness was screaming a message and humanity kept misreading it. The message was this: the universe is not what you think it is. It is not infinite in the simple sense. It is not eternal in the way you assumed. It is not static and unchanging. At least one of those foundational assumptions must be abandoned, and the darkness itself tells you which. But before that answer could be recognized, humanity needed to develop entirely new tools for understanding the cosmos, telescopes that could see beyond the Milky Way, mathematical frameworks that could describe expanding space, observations that could measure the distances and velocities of objects billions of light years away. The paradox was posed in the 16th century. Its resolution would not arrive until the 20th. 400 years of darkness, both literal and intellectual, separated the question from its answer. During those 4 centuries, the paradox sat at the boundary between philosophy and physics, a question so fundamental that it touched on the nature of reality itself. Is the universe infinite or finite? Eternal or created? Static or evolving? These are not merely astronomical questions. They are questions about the deepest structure of existence, and the astounding realization that emerged in the 20th century is that you do not need a philosopher to answer them. You do not need a theologian. You do not even need a telescope, although telescopes certainly help. All you need to do is look up on a clear night and notice that the sky between the stars is dark. That single observation, available to every human being who has ever lived, contains within it the proof that the universe has a history. The darkness is not a blank backdrop to the stars. It is not the default state of empty space. It is not a trivial consequence of missing atmosphere. The darkness between the stars is a direct, physical consequence of the fact that the universe is not what centuries of assumption claimed it to be. The cosmos is not an infinite, eternal, static stage on which stars perform forever. It is something else entirely. Something with limits. Something with a beginning. The darkness told us this all along. We simply were not listening. Consider what we have established so far. An infinite, eternal, static universe filled with uniformly distributed stars should produce a sky of unbearable brightness. No amount of interstellar dust can prevent this, because the dust itself would glow. No amount of distance can reduce it, because the shell mathematics guarantee constant brightness contribution at every radius. No amount of stellar death can eliminate it, because new stars replace the old ones in an eternal cosmos. Every reasonable objection has been tested, and everyone has failed. The darkness remains and demands explanation. The failure of these objections is itself informative. Each failed solution eliminates one possible model of the universe. Dust does not save you, so the darkness is not caused by obstruction. Distance does not save you, so the darkness is not caused by faintness. Finite stellar lifetimes do not save you in an eternal cosmos, so the darkness is not caused by temporary dimming. What is left? What assumption remains unchallenged? Time. The one thing every failed explanation has in common is that it accepts the premise of an eternal universe and tries to work within it. But the premise itself may be the problem. If the universe is not eternal, if it had a beginning, if stars have only been shining for a finite duration, then the shell argument collapses. You no longer have infinitely many shells of stars contributing light. You have a finite number, and a finite number of shells, no matter how numerous, produces a finite total brightness. A brightness that, as it turns out, is far too low to illuminate the entire sky. This is the crack in the paradox. This is the thread that, when pulled, unravels the entire ancient model of the cosmos. The darkness of the night sky is not a failure of starlight to reach us. It is evidence that the universe has not existed forever. That starlight has had only a limited amount of time to accumulate. That there is a boundary, not in space, but in time, beyond which no light has yet arrived. The paradox was not solved by discovering new physics or building better telescopes, although both eventually helped. It was solved by changing the most basic assumption about the cosmos. The universe is not eternal. It had a beginning, and because it had a beginning, the sky is dark. But the nature of that beginning, and the staggering consequences it carries for what we can and cannot see goes far deeper than anyone in the 18th or 19th century could have imagined. What scientists discovered in the 20th century did not simply resolve the paradox. It replaced a comfortable, familiar universe with something far stranger, far larger, and far more unsettling than the darkness itself. What happens next begins with the obvious follow-up question. If the universe had a beginning, what was that beginning? And what does it mean that the oldest light in the cosmos is still travelling toward us right now, filling every cubic centimetre of space, and yet remains completely invisible to human eyes? The solution to the paradox did not arrive gradually. It detonated. In the span of a few decades during the 20th century, the entire model of the universe that had sustained Western science for centuries was demolished and replaced with something so radical that many of the physicists who helped build it refused to accept what their own equations were telling them. The universe is not eternal. It is not static. It is not an infinite, unchanging stage on which stars have always performed. It had a beginning, a specific, identifiable, physically real beginning. And that single fact, more than any other, is why the night sky is dark. To understand why this resolves the paradox, start with light itself. Light is fast, faster than anything else in the physical universe. A photon leaving the surface of the sun crosses the 93 million miles to Earth in approximately 8 minutes and 20 seconds. That same photon could circle the entire planet more than 7 times in a single second. At 186,000 miles per second, light represents the absolute upper limit of speed in our reality. Nothing with mass can reach it. Nothing without mass can exceed it. It is the cosmic speed limit, woven into the structure of space-time by the laws of relativity. But fast is not the same as instantaneous, and this distinction changes everything. If light travels at a finite speed, then light from distant objects takes time to reach you. The light arriving from the sun left its surface 8 minutes ago. The light from Sirius, one of the nearest bright stars, departed 8.5 years ago. The light from the Andromeda galaxy has been travelling for roughly 2.5 million years. Every astronomical observation is an act of looking backward in time. The farther you look, the deeper into the past you see. This is not a metaphor. It is a physical consequence of the finite speed of light. When you observe a galaxy 10 billion light-years away, you are seeing it as it existed 10 billion years ago. The photons hitting your telescope are 10 billion-year-old messengers, carrying information about conditions that prevailed when the universe was young. Now, connect this to the paradox. If the universe has a finite age, then light has only had a finite amount of time to travel. There is a maximum distance from which any photon could have reached Earth since the cosmos began. Beyond that distance, stars may exist, galaxies may burn, but their light is still in transit. It has not arrived. It will not arrive for millions, billions, perhaps trillions of years, depending on how far away those sources are. The sky is dark in those directions, not because nothing is there, but because the light from what is there has not had enough time to cross the intervening space. This demolishes the shell argument from the paradox. In an infinite, eternal universe, you have infinitely many shells of stars, each contributing the same net brightness. But in a universe with a finite age, you have only a limited number of shells from which light has had time to reach you. The shells beyond that time horizon contribute nothing. Zero light, complete darkness. The sum is finite rather than infinite, and that finite sum turns out to be far too small to illuminate the entire sky. The darkness between the stars is not an anomaly. It is a direct mathematical consequence of the universe having a birthday. The question then becomes unavoidable. When was that birthday? How old is the universe? And how do we know? The first clue came not from observation but from mathematics. In 1922, a Russian physicist named Alexander Friedmann examined the equations of Einstein's general relativity and discovered something Einstein himself had missed. The equations did not describe a static universe. They described a dynamic one. Space itself could expand or contract over time. A universe governed by general relativity was not sitting still. It was moving. Friedmann's solutions showed that a universe filled with matter would naturally evolve, either growing larger or collapsing inward. depending on its density and initial conditions. A static universe was possible only if you added a special balancing term, a cosmological constant, to hold everything in place. Einstein had done exactly that, inserting the constant into his equations specifically to prevent them from predicting an expanding or contracting cosmos. He believed the universe was eternal and unchanging, and he adjusted the mathematics to match that belief. But the mathematical prediction of an expanding universe did not arrive in isolation. Years before Friedman solved Einstein's equations, an American astronomer was quietly assembling the observational evidence that would confirm exactly what the mathematics implied. His name was Vesto Slipher, and he worked at Lowell Observatory in Flagstaff, Arizona. Beginning in 1912, Slipher began measuring the spectra of what were then called spiral nebulae, fuzzy smudges of light whose nature was still debated. Were they gas clouds within the Milky Way, or were they entire galaxies far beyond it? Nobody knew for certain, but Slipher could measure their light, and what he found was extraordinary. Almost every spiral nebula he observed showed its spectral lines shifted toward the red end of the spectrum. This meant they were moving away from us, not just a few of them, not a random half. Nearly all of them, receding at velocities that in some cases exceeded 1,000 kilometers per second. Slipher presented his results at scientific meetings and published them in journals, but the full significance of what he had found was not yet clear. The concept of an expanding universe did not exist in mainstream science. There was no theoretical framework to explain why distant objects should be systematically rushing away in every direction. Slipher had the data. He did not yet have the interpretation. That interpretation came when Edwin Hubble, working at the Mount Wilson Observatory with what was then the most powerful telescope on Earth, combined Slipher's velocity measurements with his own painstaking distance estimates. Hubble used a class of pulsating stars called Cepheid variables to determine how far away the spiral nebulae actually were. These stars brighten and dim at rates directly related to their intrinsic luminosity, making them reliable cosmic distance markers. By identifying Cepheids within the nebulae and comparing their apparent brightness to their known true brightness, Hubble could calculate the distance to each nebula with unprecedented accuracy. The result was the discovery that changed cosmology forever. When Hubble plotted distance against recession velocity, the relationship was unmistakable. The farther away a galaxy was, the faster it was moving away from us. The pattern was linear, clean, and universal. It was not a quirk of a few objects. It was a law governing the entire observable cosmos. Space itself was expanding. The reaction from the scientific community was not immediate acceptance. It was resistance, deep, institutional, philosophical resistance. The idea of an expanding universe implied a beginning, and a beginning implied that the cosmos had not always existed. This disturbed physicists and astronomers on multiple levels. An eternal universe was intellectually comfortable. It required no explanation for how or why the cosmos began. It avoided the uncomfortable question of what came before. An expanding universe that started from a single dense state demanded answers that physics in the 1930s was not yet prepared to give. Einstein himself initially rejected the idea. His cosmological constant had been inserted into the equations of general relativity precisely to prevent them from predicting expansion. When confronted with Hubble's evidence, Einstein was forced to abandon the constant and accept what his own equations had been telling him all along. The universe was not static. It never had been. The mathematics had been correct from the start. It was the physicist who had flinched. But the resistance did not end with Einstein. In 1948, three physicists working in Britain, Fred Hoyle, Hermann Bondi, and Thomas Gold, proposed an alternative model called the steady-state theory. In their version of the cosmos, the universe was indeed expanding, but it had no beginning. New matter was continuously created throughout space, at a rate just sufficient to maintain a constant average density as the universe grew. The cosmos had always existed and would always exist. It was eternal, self-replenishing, and required no Big Bang. The steady-state theory was elegant. It was philosophically appealing, and it was taken seriously by a significant portion of the scientific community for nearly 2 decades. The debate between Big Bang and steady-state cosmology was not a fringe argument. It was the central controversy in 20th-century cosmology. Both models could explain the observed expansion. Both could account for the distribution of galaxies. The question was whether the universe had a beginning or whether it had always been, and for years the evidence was insufficient to distinguish between them. What settled the debate was the cosmic microwave background. The steady-state model predicted no such radiation. If the universe had always existed at roughly the same temperature and density, there was no reason for a uniform bath of ancient microwave photons to fill all of space. Only the Big Bang model predicted it, and when Penzias and Wilson detected it in 1965, the steady-state theory collapsed. The universe had a beginning, the evidence was incontrovertible, and the darkness of the night sky, which had puzzled astronomers for 4 centuries, finally had its explanation rooted in confirmed observation rather than speculation. Even before Hubble published his 1929 results, the theoretical framework for what he would find was already taking shape. A Belgian physicist and Catholic priest named Georges Lemaitre had taken Friedmann's mathematics further in 1927. Lemaitre proposed that if the universe is expanding now, then running the expansion backward in time leads to a point where all matter and energy were concentrated in a single primordial state of extraordinary density and temperature. He called this the primeval atom. The universe, Lemaitre argued, began in a moment of creation and has been expanding ever since. Hubble's observations gave this radical idea its observational foundation. The relationship Hubble confirmed, now called the Hubble-Lemaitre law, was the observational signature of an expanding universe. The cosmos was stretching, carrying galaxies apart. The galaxies were not flying through space away from a central explosion. Space between the galaxies was growing, increasing the distance between them without any of them needing to move through their local region of space at all. If the universe is expanding now, it was smaller in the past. Reverse the expansion and you eventually arrive at a state where all the matter and energy in the observable cosmos was compressed into an unimaginably small, hot, dense point. That initial state, and the explosive expansion that followed it, is what scientists call the Big Bang. The term itself was coined somewhat mockingly by the British astronomer Fred Hoyle during a radio broadcast in 1949. Hoyle favoured a competing model in which the universe had no beginning and existed in a steady state forever. He intended Big Bang as a dismissal. Instead, it became the name of the most successful cosmological model in the history of science. The Big Bang is not an explosion in space. It is an expansion of space. There is no centre point where the bang happened. There is no edge spreading outward into pre-existing emptiness. Space itself came into being and has been stretching ever since. Every point in the universe was once on top of every other point. The expansion did not happen at one location. It happened everywhere simultaneously. This is one of the hardest aspects of Big Bang cosmology for human intuition to absorb, but it is what the mathematics demand and what the observations confirm. The age of the universe has been measured with remarkable precision. Data from the Planck satellite, which mapped the cosmic microwave background radiation in extraordinary detail between 2009 and 2013, combined with observations of the expansion rate and the large-scale distribution of galaxies, yield a consistent answer. The universe is approximately 13.8 billion years old. That number has been cross-checked using multiple independent methods and datasets. The uncertainty is less than 1%. We know when the universe began with a confidence that would have been unimaginable a century ago. 13.8 billion years is an enormous span of time by any human standard, but it is not infinity. And that is what matters for the paradox. In 13.8 billion years, light can travel only so far. The observable universe, the sphere of space from which light has had time to reach Earth, has a radius of approximately 46.5 billion light-years. That number is larger than 13.8 billion because space has been expanding during the time the light was travelling. Photons that left a distant galaxy 13 billion years ago have been riding through stretching space for all that time. The galaxy that emitted them is now much farther away than it was when the light departed. The result is an observable sphere, roughly 93 billion light-years in diameter. Beyond that sphere, the universe almost certainly continues. There is no reason to believe space ends at our observational horizon, but we cannot see beyond it. The light from whatever lies past the horizon has not had time to arrive. Those regions are real. They contain matter and energy and structure, but they are invisible to us. Not because they are hidden behind some barrier or blocked by some obstacle. They are invisible because the universe is too young for their light to have crossed the gap. This is the resolution to Olbers' paradox, and it is worth stating plainly. The sky is dark at night because the universe had a beginning. Light from distant stars has only had a finite time to travel. Beyond a certain distance, no light has arrived. Most lines of sight through the cosmos do not terminate on a star, because the stars along those lines are too far away for their photons to have reached us yet. The darkness between the stars is not emptiness, it is time. It is the visible signature of a universe that is 13.8 billion years old rather than infinitely old. Every dark gap in the night sky is a region of space whose light is still en route. But the resolution does not stop here. Because the universe did not simply appear 13.8 billion years ago with stars already burning. The early cosmos was a radically different place, and what happened during its first few 100,000 years created something that still fills every cubic centimetre of space today. In the first moments after the Big Bang, the universe was unimaginably hot. Temperatures in the first second exceeded 10 billion degrees. Matter existed not as atoms or molecules, but as a screaming plasma of subatomic particles, protons, neutrons, electrons, photons, neutrinos, all smashed together in a state of such extreme energy that stable structures could not form. Photons could not travel freely. Every time a photon was emitted, it was almost immediately absorbed or scattered by the dense sea of charged particles surrounding it. Light was trapped. The universe was opaque. But even within this opaque furnace, the universe was not standing still. It was evolving, passing through distinct physical phases as it expanded and cooled, each phase leaving its own permanent mark on the cosmos we observe today. In the first fraction of a second, temperatures exceeded trillions of degrees. Quarks and gluons, the fundamental building blocks of protons and neutrons, existed as a free plasma too energetic to bind together. As the universe expanded and cooled past roughly 2 trillion degrees, quarks combined into protons and neutrons for the first time. Matter in the form we recognize, particles with defined identities and stable internal structure, had come into existence. The universe was less than 1/1,000,000th of a second old. Within the first 3 minutes, something remarkable happened. The temperature dropped to approximately 1 billion degrees, cool enough for nuclear fusion to occur but still hot enough to sustain it. Protons and neutrons began combining into the lightest atomic nuclei. Deuterium formed first, a nucleus containing 1 proton and 1 neutron. Then helium-3, then helium-4, then trace amounts of lithium-7. This process, called primordial nucleosynthesis, lasted only a few minutes before the expanding universe cooled below the temperature required to sustain fusion. The window closed, the nuclear reactions stopped, and the ratio of hydrogen to helium produced in those 3 minutes, roughly 75% hydrogen and 25% helium by mass, was locked in permanently. This prediction is one of the most powerful confirmations of the Big Bang model. When astronomers measure the chemical composition of the oldest, most pristine gas clouds in the universe, clouds that have never been enriched by stellar nucleosynthesis, they find exactly the ratio the Big Bang predicts: 75% hydrogen, 25% helium, trace amounts of deuterium and lithium. The numbers match to within the precision of the measurements. The universe carries the chemical fingerprint of its own first minutes, written in the abundances of its lightest elements. After nucleosynthesis ended, the universe entered a long era dominated by radiation. For roughly the next 47,000 years, the energy density of photons exceeded the energy density of matter. Light ruled the cosmos. The universe was a blinding, seething fog of radiation, far too hot and energetic for atoms to form. Matter existed as a plasma of bare atomic nuclei and free electrons, buffeted by photons in every direction. Structures could not form. Gravity could not pull matter together because the pressure of radiation blasted apart any concentration before it could grow. The universe was smooth, hot, and featureless. Then, gradually, as expansion continued and temperatures dropped, matter began to dominate. The energy density of radiation fell faster than the energy density of matter, because the expansion of space stretches the wavelength of photons, reducing their individual energy. Matter, by contrast, simply thins out as space grows, without each particle losing energy. Eventually, matter's total energy density surpassed radiation's. Gravity began to matter. The first faint seeds of cosmic structure, tiny density variations imprinted during the earliest moments of the universe, started to grow. Regions slightly denser than average pulled in a little more material from their surroundings. The universe was preparing to build something, but it could not start building until the fog cleared. Imagine being inside a fog so thick and so bright that you cannot see your own hand in front of your face. Not because the fog is dark, but because it glows in every direction with blinding intensity. Every point around you emits light, and every point absorbs it. You are immersed in a luminous wall of radiance with no depth, no distance, no structure visible at all. That was the early universe, a glowing, opaque furnace of plasma filling all of space, with no transparent gaps anywhere. This state persisted for approximately 380,000 years. During that time, the universe expanded and cooled. The temperature dropped steadily as space stretched, and the energy density decreased. But the plasma remained opaque because the temperature was still high enough to keep electrons stripped away from atomic nuclei. As long as free electrons filled space, photons could not travel more than a short distance before scattering off one of them. Light was effectively imprisoned. Then something changed. At around 380,000 years after the Big Bang, the temperature of the universe dropped below approximately 3,000 degrees. This was the threshold at which electrons could finally combine with protons to form neutral hydrogen atoms. The process is called recombination, a somewhat misleading name because the electrons and protons had never been combined before. It was not a reunion, it was a first marriage. When the electrons were captured by atomic nuclei, the free charged particles that had been scattering photons suddenly vanished. The fog cleared, space became transparent, and the light that had been trapped in the plasma was released all at once across the entire universe. Every point in space simultaneously became see-through. Photons that had been bouncing helplessly between charged particles were suddenly free to travel in straight lines across the cosmos. The universe went from opaque to transparent in a cosmic eye blink, and the light that was released in that moment has been traveling ever since. That light is still here. It did not dissipate, it did not fade into nothing. It has been crossing the universe for 13.4 billion years, stretched by cosmic expansion, cooled by the relentless growth of space, but never destroyed. It fills every cubic centimeter of the cosmos. It arrives from every direction in the sky. It is the oldest light in existence, the first light that was ever free to travel, the afterglow of the moment the universe became transparent. Scientists call it the cosmic microwave background, and we have already seen how its detection in 1965 ended the steady-state debate. But the story of how it was actually found deserves telling, because it reveals just how close humanity came to missing the most important signal in the history of science. The discovery was an accident. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Labs in Holmdel, New Jersey. The antenna had been built for satellite communication experiments. Penzias and Wilson were trying to calibrate it for radio astronomy observations, but they kept detecting a persistent low-level noise that they could not eliminate. The noise came from every direction in the sky. It did not change with the seasons. It did not correspond to any known radio source. They checked the equipment. They rebuilt components. They famously cleaned pigeon droppings from inside the antenna horn, suspecting the birds might be the source of the interference. Nothing worked. The noise persisted. What Penzias and Wilson had detected, without realizing it at first, was the cosmic microwave background. The signal they could not eliminate was the afterglow of the Big Bang itself, filling the sky in every direction with faint microwave radiation at a temperature of approximately 2.7 Kelvin, just a few degrees above absolute zero. The discovery earned them the Nobel Prize in Physics in 1978 and stands as one of the most important observations in the history of cosmology. Here is what makes the cosmic microwave background so extraordinary and so directly connected to the darkness of the night sky. When this light was first released 380,000 years after the Big Bang, it was not microwave radiation. It was visible light. The universe at that moment had a temperature of roughly 3,000 degrees, similar to the surface of a cool red star. The light flooding space was a deep orange-red glow, visible to any hypothetical eye that might have been watching. The entire universe glowed like the inside of a furnace. Every direction would have been luminous. There would have been no darkness anywhere. But the universe kept expanding, and as space stretched, so did the light travelling through it. The wavelengths of those ancient photons grew longer and longer as the cosmos expanded around them. Orange light became red. Red became infrared. Infrared became microwave. Over 13.4 billion years of cosmic expansion, the wavelength of the primordial light stretched by a factor of roughly 1,100. What was once a fiery glow visible to the naked eye is now a faint hiss of microwave radiation detectable only by specialized instruments. The cosmic microwave background is everywhere. Right now, in the room where you are sitting, photons from the Big Bang occupy every cubic centimeter of space around you, hundreds of them in every tiny volume, passing through your body continuously, filling every gap between every atom you are made of. They are the oldest photons in existence, survivors of the first moment the universe became transparent, still traveling, still carrying information about conditions nearly 14 billion years ago, and you cannot see a single one of them. Your eyes are completely blind to microwave radiation. The ancient glow of creation washes over you every second of every day, and you perceive nothing. This is not a small detail. It is central to understanding why space looks dark. The universe is not empty of light. It is saturated with light. The cosmic microwave background is the most perfect blackbody radiation ever measured. Satellites like COBE, launched in 1989, the Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, launched in 2009, have mapped this radiation across the entire sky with extraordinary precision. The measurements reveal a universe bathed in ancient photons whose temperature is uniform to within a few hundred thousandths of a degree. The sky is glowing. It has always been glowing, but the glow has been stretched by expansion into a wavelength regime that human biology cannot detect. But the cosmic microwave background is not perfectly uniform, and the imperfections are arguably more important than the uniformity itself. When the COBE satellite made the first precise full-sky map of the cosmic microwave background in the early 1990s, it revealed tiny temperature variations, fluctuations of roughly 1 part in 100,000 from the average temperature. Some spots in the sky were a few millionths of a degree warmer than the mean. Others were a few millionths of a degree cooler. The variations were minuscule, almost undetectable, but they were real, and they were ancient. These temperature fluctuations are fossils. They are the imprints of density variations that existed in the universe when it was only 380,000 years old. Warmer spots correspond to regions that were very slightly denser than average at the moment of recombination. Cooler spots correspond to regions that were very slightly less dense. The differences were tiny, barely perceptible even with the most sensitive instruments humanity has ever built. But they were enough. Because gravity amplifies even the smallest imbalance. Over hundreds of millions of years after recombination, those slightly denser regions pulled in more matter from their surroundings. They grew denser still. The slightly underdense regions lost matter to their neighbours and became emptier. Gravity turned whispers into shouts. The tiny hot spots in the cosmic microwave background became the galaxy clusters, superclusters, and filaments of the cosmic web. The tiny cold spots became the cosmic voids, the vast empty regions between the filaments where almost no galaxies exist. The entire large-scale structure of the universe, every galaxy, every cluster, every wall of galaxies stretching hundreds of millions of light-years, grew from the seeds visible in the cosmic microwave background. The Planck satellite mapped these seeds in finer detail than any previous instrument, producing the most detailed portrait of the infant universe ever made. The pattern of hot and cold spots encodes fundamental properties of the cosmos. The angular size of the fluctuations reveals the geometry of space. The relative heights of different-sized fluctuations reveal the ratio of ordinary matter to dark matter. The overall pattern constrains the age of the universe, the expansion rate, the density of dark energy, and a dozen other cosmological parameters. From a faint pattern of temperature variations in ancient microwave radiation, Scientists extracted a complete census of the universe's contents. It was as if someone handed you a baby photograph, and from it you could determine not only the child's age, but the size of the house they would grow up in, the climate of the country they would live in, and the date they would die. The cosmic microwave background is not just old light, it is the blueprint from which the entire visible universe was constructed. And every gap in that blueprint, every cold spot where matter was slightly sparse, corresponds to a region where galaxies did not form, where the sky remains dark, where the emptiness between structures traces back to a quantum fluctuation in the first moments of creation. The darkness between galaxy clusters today was predetermined by conditions in the universe when it was less than 400,000 years old. The dark sky you see tonight was written into the cosmic microwave background nearly 14 billion years ago. If your eyes could see microwave radiation, the night sky would not be dark. It would shine in every direction with a faint, uniform glow, the cooled remnant of the moment the universe first became transparent. There would be no darkness between the stars. The background would fill every gap, every void, every apparently empty patch of sky with the afterglow of the Big Bang. The darkness you perceive is real to your retinas, but it is not real to a microwave detector. To a radio telescope, the sky is luminous everywhere. This realization carries a disturbing implication. When we say space is dark, we are making a statement about human perception, not about the physical contents of the universe. The cosmos is filled with radiation. It has been filled with radiation since 380,000 years after the Big Bang. The radiation has never gone away. It has simply changed form. It has been stretched and cooled until it occupies a part of the electromagnetic spectrum that our eyes were never built to register. The darkness we see when we look at the night sky is a biological limitation masquerading as a physical fact. But the cosmic microwave background is not the only light that has been rendered invisible. The expansion of space does not affect only the oldest photons. It affects all photons traveling through the cosmos over long distances. And this brings us to a second mechanism that deepens the darkness, one that takes perfectly visible starlight from distant galaxies and systematically erases it from human perception. The cosmic microwave background proved that the universe had a beginning. It confirmed the Big Bang model with a precision that left no room for reasonable doubt. It showed that space was once filled with visible light that has since been stretched beyond the range of human sight. And it revealed that what we experience as darkness is not the absence of light, but the presence of light we cannot see. Yet the cosmic microwave background is ancient. It comes from a single epoch, a single moment in cosmic history. What about the light from stars and galaxies that formed later? What about the photons emitted by galaxies 5 billion, 8 billion, 12 billion years ago? Those galaxies were shining in visible light when their photons departed. Bright, luminous, unmistakable. But the photons from the most distant among them have been travelling through expanding space for billions of years. And during that journey, something happened to them. Something that took perfectly good visible light and made it disappear from the spectrum our eyes can process. That something is not destruction, it is not absorption, it is not scattering, it is something more subtle and more profound. The universe itself changed the colour of the light while it was in transit, and the mechanism behind this transformation is the same force that resolved the paradox in the first place: expansion. The stretching of space, the relentless growth of the cosmos that turned the glowing furnace of the early universe into the cold, dark sky we see today. What comes next reveals how that stretching works, what it does to every photon crossing the cosmos, and why the sky we see tonight is missing light that is still out there, still travelling, still carrying its ancient message, but arriving in a language our eyes were never designed to read. Every photon in the universe carries a signature. It has a wavelength, a measurable distance between one crest of the wave and the next, and that wavelength determines everything about how we perceive it. Short wavelengths look blue or violet to human eyes. Longer wavelengths look red. Stretch the wavelength further, and the light slides past red into infrared, a form of radiation your skin can feel as heat, but your eyes cannot detect at all. Stretch it further still, and you reach microwaves, then radio waves, then wavelengths so long that individual crests are separated by meters rather than fractions of a millimeter. All of these are light. All of them are electromagnetic radiation traveling at the same speed through the vacuum of space. The only difference is wavelength, and that difference determines whether you can see them. Human vision operates within an extraordinarily narrow band. The shortest wavelength your retina can register is approximately 380 nanometers at the violet edge of the visible spectrum. The longest is approximately 700 nanometers at the red edge. Between those two boundaries lies the entirety of the visual universe. Every color you have ever seen, every sunset, every star, every photograph, every painting, all of it fits within a window of roughly 320 nanometers. Now consider the full electromagnetic spectrum. Radio waves can have wavelengths measured in kilometers. Gamma rays have wavelengths smaller than the nucleus of an atom. The total range of electromagnetic radiation spans more than 20 orders of magnitude, from wavelengths shorter than a trillionth of a meter to wavelengths longer than the diameter of a planet. Within that staggering range, the slice you can see with your unaided eyes occupies less than 1/10 trillionth of the whole. You are looking at the universe through a crack in a door, and calling the sliver you see the entire room. The reason your eyes are tuned to that particular crack is not cosmological, it is biological. And it is, in a quiet way, one of the great ironies of human existence. Our sun emits radiation across a broad range of wavelengths, from radio waves to X-rays. But its peak output, the wavelength at which it radiates the most energy, falls almost exactly in the center of the visible spectrum, near the boundary between green and yellow light. This is not a coincidence, it is evolution. Over hundreds of millions of years, the eyes of terrestrial animals were shaped by natural selection to be most sensitive to the wavelengths most abundantly available from the star that illuminates their planet. We see visible light because that is what the sun produces most of. Our retinas are tuned to our local star the way a radio receiver is tuned to a local station. This means that human vision was never optimized for understanding the universe. It was optimized for surviving on the surface of one rocky planet, orbiting one medium-sized star in one spiral arm of one galaxy, finding ripe fruit, detecting predators in tall grass, navigating terrain under daylight. These were the selection pressures that built your visual system. The cosmos and its full electromagnetic output played no role in the process. Evolution did not care that the cosmic microwave background existed. It did not care that distant galaxies were radiating in the infrared. It cared about whether you could spot a snake in the undergrowth before it struck. The result is that the very star responsible for making life possible on Earth is also the reason human eyes are blind to most of the light in the universe. The sun gave us sight, but it gave us sight calibrated to itself, not to the cosmos. Every wavelength outside that narrow solar-optimized window is invisible to us, and the overwhelming majority of the radiation filling the universe falls outside that window. The darkness of the night sky is, in part, a consequence of the fact that our eyes were built for a world, not for a universe. This would not matter much if the universe only produced visible light, but it does not. Stars emit across the full spectrum, from radio waves to gamma rays. Gas clouds radiate in infrared. Neutron stars pulse in X-rays. The cosmic microwave background floods space with microwave photons. The universe is radiating at every wavelength simultaneously, and the vast majority of that radiation is invisible to you. When you look at the night sky and see darkness between the stars, you are seeing only the absence of visible photons in those directions. You are not seeing the absence of all photons. The distinction is enormous, and it sits at the heart of why cosmic darkness is so profoundly misunderstood. The mechanism that makes this distinction matter on a cosmic scale is redshift. We have established that the universe is expanding, but now we need to examine what expansion does to light in transit, because this is the process that takes perfectly visible starlight and systematically removes it from the spectrum your eyes can detect. Imagine plucking a guitar string. The string vibrates and produces a tone at a specific pitch. Now imagine that while the string is vibrating, someone slowly stretches the guitar, pulling the neck away from the body. As the string gets longer, the pitch drops. The vibrations become slower. The wavelength of the sound increases. If you stretch the guitar far enough, the pitch drops below the lowest frequency your ear can hear. The string is still vibrating. The sound waves are still propagating through the air, but you perceive silence. The sound has not been destroyed. It has been stretched below your threshold of hearing. Light traveling through expanding space undergoes the same transformation. A photon emitted by a distant galaxy has a specific wavelength when it begins its journey. But during the millions or billions of years that photon spends crossing space, the universe expands. The fabric of space-time stretches, and the wavelength of the photon stretches along with it. A photon that was emitted as blue light might arrive as red light. A photon emitted as red light might arrive as infrared. A photon emitted as infrared might arrive as microwave radiation. The longer the photon travels through expanding space, the more its wavelength stretches. The more its wavelength stretches, the further it shifts from the visible range. And once it crosses the threshold of 700 nanometers, it vanishes from human perception entirely. This process is called cosmological redshift, and it is not the same as the Doppler effect, although the two are often confused. The Doppler effect occurs when a source of light moves through space relative to an observer. Cosmological redshift occurs because space itself is expanding between the source and the observer. The galaxy that emitted the light may not be moving through its local region of space at all. It is simply being carried away by the growth of space itself. The wavelength stretches not because the galaxy is fleeing, but because the medium the light travels through is growing while the light is in transit. Imagine sending a beam from a flashlight down an impossibly long hallway. While the light is traveling, the hallway itself begins to stretch. It gets longer. The walls spread apart. The floor and ceiling recede. The light keeps moving at the same speed, but the space it must cross keeps growing. By the time the beam reaches the far wall, the hallway is much longer than it was when the light departed, and the light itself has been stretched along with the hallway. Its wavelength is longer, its energy is lower, its color has shifted. In the real universe, the hallway is space, the flashlight is a distant galaxy, and the stretching is cosmic expansion. The further away a galaxy is, the longer its light spends traveling through expanding space, and the more its wavelength is stretched by the time it arrives. Galaxies a few 100 million light-years away show modest redshift. Their light has been stretched slightly, shifted a small amount toward the red end of the spectrum. But galaxies billions of light-years away show dramatic redshift. Their light has been traveling for so long through so much expanding space that it has been stretched far beyond the visible range. It arrives as infrared radiation, invisible to human eyes, detectable only by specialized instruments. The numbers make this concrete. A galaxy at a redshift of 1 has had its light stretched to twice the original wavelength. Light that left that galaxy as blue at 400 nanometers arrives at 800 nanometers in the near infrared. Your eyes cannot see it. A galaxy at a redshift of 5 has had its light stretched to 6 times the original wavelength. Visible light emitted by the stars in that galaxy, light that left as familiar blues and whites, arrives in the infrared, entirely beyond what human eyes can detect. A galaxy at a redshift of 10 has had its light stretched to 11 times the original wavelength. Visible light, emitted at 500 nanometers, arrives at 5,500 nanometers, deep in the infrared, invisible to any biological eye that has ever evolved on Earth. And the most distant confirmed galaxy known to science, an object designated MOME Z14, has a redshift of 14.4. Its light has been stretched to more than 15 times the original wavelength. Radiation that was emitted as ultraviolet light by the youngest, hottest stars in that galaxy arrives at wavelengths longer than 1.5 microns. Below that threshold, the galaxy does not exist in light at all. No optical telescope, no matter how powerful, can see it. It is completely invisible in every wavelength, shorter than the near-infrared. If you pointed the most powerful optical telescope ever built directly at MOME Z14, you would see nothing. Pure darkness, an empty patch of sky, and you would be wrong about every conclusion you drew from that darkness. This is where the James Webb Space Telescope transformed our understanding of the cosmos. The James Webb Space Telescope was not designed to see visible light the way the Hubble Space Telescope does. It was designed specifically to see infrared radiation, the very wavelengths into which ancient starlight has been redshifted by billions of years of cosmic expansion. Its primary mirror, 6.5 meters across and coated in a microscopically thin layer of gold, optimized for infrared reflection, collects light that human eyes are completely blind to. Its instruments, the near-infrared camera and the mid-infrared instrument, detect photons at wavelengths ranging from 0.6 of a micron to 28.5 microns, a range that extends far beyond the red edge of human vision. When the James Webb Space Telescope looks at a patch of sky that appears dark to an optical telescope, it sees something astonishing. That apparently empty region is crowded with galaxies. Thousands of them, tens of thousands, ancient galaxies whose light left them when the universe was only a few 100 million years old. Galaxies that have been invisible to every telescope humanity has ever built before this one. Not because they are faint, but because their light has been shifted to wavelengths no previous instrument was designed to capture. The darkness was never emptiness. It was a limitation of our instruments and our biology. The James Webb Advanced Deep Extragalactic Survey, one of the telescope's flagship programs, has catalogued thousands of galaxies at extreme redshifts in patches of sky that appeared blank to Hubble. Some of these galaxies existed when the universe was less than 3% of its current age. They are bright, compact, and in many cases more massive and more structured than theoretical models predicted was possible at such early times. Their discovery has challenged assumptions about how quickly galaxies can form, and has opened entirely new questions about the conditions in the early cosmos. But the most fundamental thing the survey revealed is not about galaxy formation. It is about perception. Those galaxies were always there. Their light was always arriving. We simply could not see it because we were looking in the wrong part of the spectrum. This realization forces a complete reframing of what cosmic darkness means. When you look at the night sky and see dark space between the stars, you are not looking at emptiness. You are looking at a universe that is radiating in wavelengths your eyes cannot register. The cosmic microwave background contributes roughly 400 photons per cubic centimeter throughout all of space. Infrared radiation from ancient galaxies fills the gaps between visible stars. Radio waves from pulsars and synchrotron radiation from galactic magnetic fields permeate the cosmos. X-rays pour from accretion disks around black holes and from the superheated gas in galaxy clusters. Gamma rays erupt from the most violent events in the universe. All of this radiation is real, all of it is present, and almost none of it is visible to you. The visible universe, the universe you experience when you look up at night, is a tiny fraction of the actual electromagnetic universe. You see the stars that happen to emit enough visible photons in your direction to trigger your retinal cells. Everything else, the vast majority of cosmic radiation, passes through your field of view undetected. The darkness you perceive is not a property of the universe, it is a property of your eyes. This carries a specific and measurable consequence for Olbers' paradox. Even if you could somehow overcome the finite age limitation, even if the universe were old enough for light from every star in every direction to have arrived, the sky would still appear dark to human eyes because much of that light has been redshifted out of the visible band. The expansion of space systematically converts visible photons into invisible ones. The longer a photon travels, the more it stretches. The more distant the source, the more its light is shifted beyond human perception. Redshift operates like a filter that preferentially removes the most distant sources from your visual experience, while leaving their radiation intact in other parts of the spectrum. Consider what the night sky would look like if your eyes could detect the full electromagnetic spectrum. The cosmic microwave background would fill the entire sky with a faint uniform glow. The infrared sky would reveal millions of galaxies currently invisible to the naked eye. X-ray and gamma-ray sources would blaze in regions that appeared dark in visible light. Radio emissions would trace magnetic structures spanning millions of light years. The sky would not be dark. It would be luminous, layered, complex, glowing in every direction with radiation from every epoch of cosmic history. The darkness that feels so natural to human experience is an artifact of our biology, a consequence of evolving eyes that respond to only one narrow sliver of the radiation that saturates the cosmos. But it is also important to be precise about what this does and does not explain. Redshift does not create darkness on its own. Even if every distant galaxy's light has been shifted to infrared, the nearby stars in our own galaxy still emit plenty of visible light. The reason you see dark gaps between those nearby stars is not primarily because of redshift. It is because of the finite age effect we explored earlier. There are not enough nearby stars to fill every sightline. Most lines of sight through the Milky Way pass between stars without hitting one. The darkness you see in those gaps is the finite age darkness, the consequence of a universe too young for infinitely many shells of stars to fill the sky. Redshift adds a second layer of darkness on top of the first. It takes the light from the most distant galaxies, light that is arriving right now after traveling for billions of years, and removes it from your perception. This means that even if you could count every visible photon arriving from every direction, you would still be missing the enormous contribution from sources whose light has been stretched past 700 nanometers. The visible sky underestimates the total light in the universe by a factor that grows with distance. Close galaxies contribute most of their light in the visible range. Moderately distant galaxies contribute in the near-infrared. The most distant galaxies contribute only in the mid-infrared or longer wavelengths. By the time you reach the cosmic microwave background, the light has been stretched by a factor of more than 1,000 and occupies wavelengths measured in millimeters rather than nanometers. The two mechanisms work together. The finite age of the universe limits how many sources can contribute light at all. Cosmic expansion then takes a substantial fraction of the light that does arrive and shifts it beyond the visible range. The combined result is a sky that appears dark to human eyes despite being saturated with radiation across the full electromagnetic spectrum. Darkness is a collaboration between time and expansion, between the youth of the cosmos and the relentless stretching of space. There is one more layer worth understanding. Not all of the invisible radiation in the cosmos comes from redshifted starlight. Some of it was never visible in the first place. Stars emit across the full spectrum, but many astronomical objects emit primarily or exclusively outside the visible range. Molecular gas clouds in interstellar space radiate in the far infrared and sub-millimeter wavelengths as their constituent molecules vibrate and rotate. Dust grains heated by nearby stars glow in the mid-infrared. Pulsars, the rapidly spinning remnants of dead massive stars, emit pulsed beams of radio waves. Accretion disks around black holes convert gravitational energy into X-rays with efficiencies that dwarf nuclear fusion. Gamma-ray bursts, the most energetic explosions in the universe, release more energy in a few seconds than the sun will produce in its entire lifetime, and nearly all of that energy comes out as gamma radiation invisible to the naked eye. The universe is not merely emitting light that gets redshifted beyond your vision. It is generating vast quantities of radiation that was never in the visible range to begin with. These sources contribute their own form of invisible luminosity to the cosmos, adding to the total electromagnetic energy filling space, while remaining completely undetectable to unaided human perception. Scientists have measured the total radiation content of the universe across all wavelengths. The result is called the extragalactic background light, the sum of all photons that have been emitted by all sources throughout cosmic history. The extragalactic background light spans from radio waves to gamma rays and represents the accumulated output of every star, every galaxy, and every energetic process that has ever occurred. When measured across the full spectrum, the universe is far from empty. It is radiating continuously at every wavelength, a cosmos blazing with energy from edge to edge of the observable volume. The darkness you see at night is not a feature of this radiation field. It is a feature of the detector you are using to observe it, which happens to be a pair of biological organs sensitive to a range of wavelengths narrower than the thickness of a human hair compared to the width of the Pacific Ocean. The James Webb Space Telescope opened the infrared window, but other observatories have opened other windows. The Chandra X-ray Observatory revealed a violent universe of colliding galaxy clusters and feeding black holes. Radio telescopes like the Square Kilometre Array precursors are mapping magnetic structures and hydrogen gas across billions of light years. Gamma-ray observatories have detected radiation from the most extreme events in the cosmos. Each new window reveals a universe teeming with activity in regions that looked silent and dark in visible light. Each instrument peels back another layer of the electromagnetic spectrum and finds the cosmos luminous beneath. The pattern is consistent and unambiguous. Every time scientists build a detector sensitive to a new wavelength range and point it at apparently dark sky, they find light. Not always starlight, not always from familiar sources, but radiation, energy, Photons that have been traveling through the cosmos for millions or billions of years, arriving at Earth continuously, passing through the atmosphere, through the walls of your home, through your body, carrying information about the state of the universe at the moment they were emitted. The darkness is not silence. It is a conversation happening in frequencies you were never equipped to hear. The most distant objects the James Webb Space Telescope has revealed existed when the universe was a fraction of its current age. Their light has been travelling for over 13 billion years. During that journey, it crossed space that was expanding, stretching the wavelengths further and further from the visible range. By the time those photons arrived at the telescope's mirror, they carried the signature of a cosmos in its infancy, encoded not in the blue and white wavelengths the original stars emitted, but in the infrared wavelengths the universe had stretched them into. The telescope did not discover new objects. It translated ancient light from a language our eyes cannot read into images our minds can comprehend. This translation is the key to understanding cosmic darkness. The universe has been writing messages in light since the moment it became transparent. Those messages contain the history of every star that ever burned, every galaxy that ever formed, every explosion that ever scattered heavy elements into the void. The messages are still arriving. They have never stopped arriving, but the universe wrote many of them in wavelengths that the human eye, a product of evolution on a small rocky planet orbiting a medium-sized star, was never designed to decode. The night sky is dark because we are reading only a fraction of the mail. The rest is piling up around us unseen, filling every corner of space with information we have only recently learned to access. And yet, even with our new instruments and our expanded view, there are messages we will never receive. There are regions of the cosmos from which light is travelling toward us right now, but will never arrive. Not because the light is too faint, not because it has been shifted beyond our instruments, but because the universe itself is carrying it away faster than it can cross the distance between us. The darkness of the night sky encodes something deeper than biology, deeper than redshift, deeper than the finite age of the cosmos. It encodes the existence of boundaries, horizons beyond which the universe becomes permanently inaccessible. And what those horizons reveal about the nature of reality, about what we can and cannot ever know, is the most disturbing part of this story. There is a moment in every deep investigation when the evidence stops answering your original question and begins answering a much larger one. You set out to understand a single phenomenon and discover that it is connected to something so vast that the original question becomes almost trivial by comparison. The darkness of the night sky is that kind of phenomenon. We began by asking why space looks black. The answer led through the finite age of the universe, through the expansion of space, through the stretching of light beyond human perception. But now, standing at the end of that trail, we can see that the darkness was never really about missing light. It was about something far more fundamental. The darkness is a boundary marker. It delineates what the universe has allowed us to know from what it has placed permanently beyond our reach. And the shape of that boundary tells us things about reality that no other observation can. Start with what the darkness has already revealed. The sky is dark because the universe is approximately 13.8 billion years old. That fact alone, extracted from the simple observation that the night sky is not blazing with wall-to-wall starlight, tells us the cosmos had a beginning. It tells us that time is not infinite in the backward direction. It tells us that there was a first moment, a boundary in the past before which the universe as we know it did not exist. This is not a philosophical claim. It is a physical deduction drawn from the darkness between the stars, as surely as a detective draws conclusions from evidence at a crime scene. The darkness is the evidence. The finite age is the verdict. The sky is also dark because the universe is expanding, stretching ancient light into wavelengths human eyes cannot detect. This tells us that space is not static. It is dynamic. It grows. The distances between galaxies increase over time, not because galaxies are flying apart through a fixed background, but because the background itself is changing. Space has a history. It was smaller yesterday than it is today, and it will be larger tomorrow than it is now. The darkness encodes this expansion directly. Every photon that arrives redshifted beyond the visible spectrum carries a record of how much space expanded during its journey. The darkness is a logbook of cosmic growth, written in stretched wavelengths and faded frequencies. But these two revelations, finite age and cosmic expansion, are only the beginning of what the darkness encodes. There is a third message, subtler and more disturbing than the first two. The darkness tells us that the universe has horizons, and horizons mean that there are things we will never see, never measure, never know. The concept of a cosmic horizon is simple in principle but staggering in its implications. Because the universe has a finite age and light travels at a finite speed, there is a maximum distance from which any signal could have reached Earth since the cosmos began. That distance defines the boundary of the observable universe, a sphere approximately 93 billion light-years in diameter centered on our location. Everything inside that sphere is, at least in principle, detectable. Everything outside it is not. Not because it does not exist, not because it is somehow less real than the matter and energy within our observable volume, but because the light from those regions has not had enough time to reach us. The universe beyond the horizon is real, physical, and completely inaccessible. This alone would be remarkable, but there is a complication that transforms the horizon from a temporary inconvenience into a permanent prison. The universe is not just expanding, it is expanding at an accelerating rate. Dark energy, the mysterious component that constitutes approximately 68% of the total energy content of the cosmos, drives this acceleration. Unlike matter, which slows expansion through gravitational attraction, dark energy pushes space apart with increasing force. The result is that the expansion rate of the universe is not constant, it is growing, and this growth has a devastating consequence for cosmic horizons. In a universe with accelerating expansion, the observable horizon does not simply stay where it is while we wait for more distant light to arrive. Instead, the expansion carries distant objects away from us faster than their light can approach. There are galaxies whose photons are traveling toward us right now, photons that have been in transit for billions of years that will never arrive. The space between us and those galaxies is expanding faster than the photons can cross it. Those galaxies are receding beyond our reach, not because they are moving through space, but because space itself is growing between us and them at a rate that outpaces the speed of light. This is not a violation of relativity. Nothing is traveling through space faster than light, but space itself faces no speed limit. It can expand at any rate, and at sufficient distances, the cumulative effect of that expansion exceeds the speed of light. Objects beyond this threshold, called the cosmic event horizon, are permanently disconnected from us. No signal we send can ever reach them. No signal they send can ever reach us. The disconnection is absolute, irreversible, and growing. Every second, regions of the universe that were marginally within reach slip beyond the event horizon and are lost forever. The observable universe is not growing fast enough to compensate. The boundary of what we can influence is shrinking, even as the boundary of what we can see continues to expand slowly. The universe is closing around us. The darkness of the night sky is a visible record of this closure. Every dark patch between the stars represents a direction in which the observable universe has a finite depth. Some of that depth is limited by the finite age of the cosmos. Light from beyond a certain distance has not arrived yet. Some of it is limited by redshift. Light from extremely distant sources has been stretched past the visible range and can only be detected with infrared or microwave instruments. And some of it is limited by accelerating expansion. Light from the most distant regions will never arrive at all, regardless of how long we wait or what instruments we build. Three distinct mechanisms conspire to create the darkness, and each one encodes a different physical truth about the universe we inhabit. This brings us to a consequence so disturbing that it challenges fundamental assumptions about the nature of scientific knowledge. The universe is not merely hiding information from us, it is actively destroying the evidence. Consider what happens over cosmic time as expansion accelerates. Today, we can observe galaxies numbering in the trillions scattered across the observable volume. We can detect the cosmic microwave background arriving from every direction. We can measure the expansion rate using distant supernovae and baryon acoustic oscillations. We can reconstruct the history of the cosmos from its first moments to the present. The evidence is abundant, accessible, and interpretable. We live in an era of extraordinary cosmological visibility. But that era will not last. As dark energy continues to accelerate expansion, distant galaxies will be carried beyond our observable horizon at an increasing rate. Not in a sudden vanishing, not in a dramatic extinction event, in a slow, silent recession that will play out over billions of years, galaxy by galaxy, cluster by cluster, until the sky empties of everything beyond our immediate gravitational neighborhood. The Milky Way, Andromeda, and the few dozen smaller galaxies gravitationally bound to us will eventually merge into a single large elliptical galaxy. Astronomers have already named this future merged structure Milkomeda. It will be an enormous galaxy, containing perhaps 1 trillion stars, but it will also be profoundly alone. The timeline of this isolation is specific enough to outline, and doing so makes the future darkness feel less abstract and more inevitable. At approximately 10 billion years from now, roughly double the current age of the universe, the cosmic expansion rate will have increased substantially. Galaxies currently at moderate distances will be receding at speeds well above what we observe today. The most distant galaxies visible to current telescopes will have been carried beyond the event horizon. Their light, already faint and deeply redshifted, will fade past the detection threshold and vanish from the observable sky. The census of visible galaxies will begin to shrink. At approximately 50 billion years from now, the effect will have become dramatic. The most distant galaxy clusters currently visible at billions of light years will be receding at velocities that push their light toward infinite redshift. Closer clusters will follow. The Virgo cluster, currently the nearest major galaxy cluster and a gravitational anchor for our local supercluster, will hold out longer because of its relative proximity. But even it will eventually be carried beyond the event horizon within roughly 100 billion years. It will not disappear suddenly. Instead, it will dim and redden over billions of years, like a ship sailing beyond the horizon of an ocean, growing smaller and fainter until it is simply gone. Other nearby clusters will follow: the Coma cluster, the Perseus cluster. One by one, the great concentrations of galaxies that define our cosmic neighborhood will cross the event horizon and vanish from the observable universe. At approximately 100 billion years from now, the process will be essentially complete. Every galaxy and galaxy cluster beyond the local group will have been carried past the horizon. The sky, aside from the merged structure of Milkomeda and its remaining bound satellites, will be empty. Not apparently empty, actually empty of any external source of light. Astronomers in that era will point their telescopes outward and find nothing. No distant galaxies, no large-scale structure, no cosmic web. The universe will appear to contain exactly one galaxy, surrounded by limitless void. At 1 trillion years from now, Milkomeda will be a dimmer but still living galaxy. Star formation will have long since ceased as the available hydrogen gas was consumed or expelled. The massive stars and sun-like stars will have died billions of years earlier. Only the red dwarfs will remain, the smallest and longest-lived stellar furnaces, still burning steadily on reserves of hydrogen that can sustain them for 10 trillion years or more. At 1 trillion years, these tiny embers will barely have begun their long lives. But they are not eternal. Over the following 10 trillion years, one by one, the last red dwarfs will exhaust their fuel and fade into cooling white dwarfs, slowly radiating away their residual heat into the expanding void. The galaxy will darken from within, not suddenly, but with the imperceptible patience of a candle burning down in an empty room. In 2007, physicists Lawrence Krauss and Robert Scherer published a paper examining exactly what a civilization arising in this far future would be able to determine about the cosmos. Their conclusions were striking. Such a civilization would observe a single galaxy embedded in static, empty space. Without distant galaxies to measure, they would have no evidence of cosmic expansion. Without the cosmic microwave background, they would have no evidence of a hot, dense beginning. Without observable large-scale structure, they would have no way to infer the cosmic web, dark matter distribution, or the history of structure formation. Their best cosmological model would describe an island universe, a single galaxy that had always existed in an infinite void. It would be wrong, but it would be perfectly consistent with every observation available to them. Krauss and Scherer pointed out something even more troubling. It was not merely that the evidence would be absent, the evidence would be actively contradicted by what remained. The future observers would see a galaxy full of old stars with no ongoing star formation, surrounded by empty space. The simplest explanation for this configuration, the model that best fit the data, would be a static, eternal universe containing one aging stellar system. The correct model, an expanding cosmos containing trillions of galaxies that had been carried beyond the horizon by dark energy, would seem absurdly complicated and entirely unsupported by observation. A future physicist who proposed such a model would be dismissed as a fantasist. The universe would have hidden its own history so completely that the truth would be indistinguishable from delusion. The sky around Milkomeda will be dark, not the partial darkness we see today, where the gaps between stars are broken by the faint glow of distant galaxies. True darkness. Deep, featureless, absolute darkness in every direction beyond the local gravitational neighborhood. The cosmic microwave background, which currently provides our most direct evidence of the Big Bang, will have been stretched by expansion to wavelengths so long and energies so low that no conceivable detector could register it. The ancient glow of creation will have faded below the noise floor of physics itself. The afterglow will still technically exist, but it will be indistinguishable from nothing. The specific physics of this disappearance deserves attention, because it illustrates just how thoroughly the universe erases its own evidence. The cosmic microwave background currently has a temperature of approximately 2.7 Kelvin and peaks at a wavelength of roughly 2 millimeters in the microwave band. As the universe expands, this radiation cools. The temperature drops in direct proportion to the expansion factor. When the universe is expanded by another factor of 10, the temperature will fall to approximately 0.27 Kelvin, and the peak wavelength will stretch to roughly 2 centimeters. Still detectable, in principle, by a sufficiently sensitive radio telescope. When the universe is expanded by a factor of 100, the temperature drops to 0.027 Kelvin. The peak wavelength stretches to 20 centimeters. The number of photons per cubic centimeter drops from the current 400 to less than 1. Detection becomes extraordinarily difficult even in theory. At a factor of 1000 in expansion, the temperature falls to roughly 0.0027 Kelvin, less than 0.003 of a degree above absolute zero. The peak wavelength stretches to 2 meters. Individual photons are so sparse that a detector the size of a building might wait years to capture one. The signal is still there, technically, but it is buried so deeply beneath the quantum noise floor that extracting it would require technology that may be physically impossible regardless of how advanced a civilization becomes. The cosmic microwave background does not switch off. It fades asymptotically towards zero, stretched and diluted until it becomes indistinguishable from the vacuum fluctuations of empty space itself. This is not like a radio station going off the air. It is like a radio station whose signal is being stretched and weakened continuously, the frequency dropping lower and lower, the volume falling softer and softer, until the broadcast merges with the background static of the receiver, and no amount of amplification can separate signal from noise. The message is still being transmitted, but no receiver in the universe can decode it. Now, consider what this means for a civilization that arises in Milkomeda billions of years from now. They will look out at their sky and see their own galaxy. Nothing else. They will build telescopes, survey the heavens, and catalogue every object they can find. And every observation they make will confirm a single, consistent, entirely wrong picture of the cosmos. Imagine a library containing the complete history of the universe. Now imagine that the library is on fire, but the fire is not burning randomly. It is moving methodically from shelf to shelf, carrying each book beyond the reach of the readers inside before they can finish it. The readers in the center of the library can still see the shelves nearest to them. They can read those books and learn what they contain, but the outer shelves are receding into the flames, and the books on them are being lost one by one. The readers do not see the fire. They only notice that the library seems to be getting smaller, that there are fewer shelves than there used to be, that the history they can access is shrinking while the history they have lost grows beyond recovery. We are those readers. The universe is that library. And the fire is accelerating expansion. The cosmological information available to observers in the far future will be a fraction of what we possess today. They will inhabit a universe that appears static, bounded, and alone. Their best cosmological models will describe a single galaxy floating in an otherwise empty void, and those models will be perfectly consistent with every observation available to them. They will be wrong, but they will have no way of knowing it. The evidence that would correct their error will have been erased by the expansion of space. This is not speculative fiction. This is the trajectory indicated by current observations. The accelerating expansion of the universe is confirmed by multiple independent lines of evidence. Data from the Planck satellite, from supernova surveys, from baryon acoustic oscillation measurements, and most recently from the dark energy spectroscopic instrument, all confirm that dark energy is real and that expansion is accelerating. The most recent data, released in 2025, has even raised the possibility that dark energy may not be a simple cosmological constant, but may be evolving over time, potentially strengthening. If dark energy grows stronger, the future darkening of the universe may proceed faster than current models predict. The horizon will close sooner. The evidence will be lost more quickly. The darkness will deepen on an accelerated timeline. We live in a window, a narrow, temporary window during which the universe is still young enough, still slow enough in its expansion, still transparent enough in its radiation, that we can piece together the full story of cosmic history. We can detect the cosmic microwave background and infer the Big Bang. We can observe distant galaxies and measure the expansion rate. We can use redshift to reconstruct how the universe has grown over 13.8 billion years. We can identify the fingerprints of dark energy and the acceleration of that growth. All of this is possible right now. None of it will be possible in the deep future. The window is open today. It will close. And when it closes, the darkness will be total and permanent, carrying with it every clue about the true nature of the cosmos. This realization transforms the darkness of the night sky from a curiosity into something that feels almost urgent. Every dark gap between the stars is a reminder that information is finite, that the universe does not owe us its secrets, that the evidence we rely on to understand reality is contingent on our position in cosmic time, and that position is temporary. We happen to exist during the era when the cosmic microwave background is still detectable, when distant galaxies are still visible, when the expansion rate can still be measured by comparing nearby and faraway objects. A civilization arising 100 billion years from now will have none of these advantages. They will look at a dark sky and see only their own galaxy, and they will have no way of knowing that the darkness once contained a message they could no longer read. Return now to where we started. You are looking up at the night sky. Between the stars there is darkness. You have spent this entire journey learning what that darkness contains and what it means. Let us assemble the full picture. The darkness is not emptiness. It never was. It is the visible consequence of at least 3 overlapping physical realities, each one profound on its own, and together composing a message about the nature of the universe that no other observation delivers so completely. First, the darkness tells you that the universe had a beginning. The sky is not ablaze with the light of infinitely many stars because stars have not been shining for an infinite amount of time. There was a first moment, a boundary in the past. The light from the most distant reaches of the cosmos has not had time to reach you because the cosmos itself has only existed for 13.8 billion years. The darkness between the stars is the shadow of a finite history. Second, the darkness tells you that the universe is expanding. Ancient light that was once visible has been stretched by the growth of space into wavelengths your eyes cannot detect. The cosmic microwave background, once a fiery orange glow filling the entire sky, now whispers in microwave frequencies far below the threshold of human sight. Galaxies that emitted bright, visible light billions of years ago now send us photons that arrive only in the infrared. The darkness you see is partly a gap between perceptible signals, radiation that exists all around you but falls on the wrong side of your biological detection limit. The universe is luminous. You are simply not equipped to see most of the luminosity. Third, the darkness tells you that the universe has horizons. There are regions of space from which no light will ever reach you, no matter how long you wait. Accelerating expansion is carrying those regions beyond the cosmic event horizon, severing every possible causal connection between them and you. The darkness in those directions is not temporary. It is permanent. It represents the boundary of what the universe permits you to observe. Beyond it lies reality you can theorize about but never confirm. The darkness is a wall made not of matter but of expanding space, and it is growing higher every second. These three truths, finite age, expansion, and horizons, are written in the darkness every night, available to anyone who looks up and asks the right question. They were always there. The darkness carried this message long before humanity existed, before the earth formed, before the sun ignited. The message predates every civilization, every species, every living thing that has ever looked upward and wondered. The darkness has been broadcasting since the universe became transparent 13.4 billion years ago. We are simply the first listeners on this planet to decode what it is saying. And what it is saying is terrifying. Not because the universe is hostile, not because the darkness conceals monsters or threats. The terror is subtler and more fundamental than that. The darkness tells us that reality has limits, that observation has boundaries, that the act of looking outward into space is also the act of looking backward through time, and that both directions terminate. The past has a beginning. The visible universe has an edge. The future will erase the evidence we now use to understand both. When you look at a dark patch of sky between two stars, you are not seeing nothing. You are seeing the space through which ancient photons are still traveling, stretched to invisibility by expansion. You are seeing the direction in which the observable universe runs out of depth, where the finite age of the cosmos cuts off the supply of visible starlight. You are seeing the boundary between what the universe has revealed and what it has withheld. And you are seeing a preview of the future, when that boundary will have contracted so far that the sky will show nothing at all beyond a single aging galaxy surrounded by infinite, permanent, impenetrable darkness. The cosmos is not an eternal, infinite, brightly lit room. That was the old model, the model that Olbers' paradox destroyed. The real universe is something far stranger. It is a finite bubble of visibility expanding into a vastness we may never fully map, filled with light we mostly cannot see, bounded by horizons that are receding beyond our reach, and slowly, inexorably, going dark. The night sky is not a backdrop, it is a document. It records the age of the universe in the gaps between the stars. It records the expansion of space in the reddened light of distant galaxies. It records the existence of cosmic horizons in the regions from which no photon will ever arrive. It is the most information-dense surface in human experience, and most people walk beneath it every night without reading a single line. But now you know how to read it. The next time you stand outside after dark and look up at the sky, you will see the same stars everyone else sees, the same points of light scattered across the same black expanse. But you will also see what the darkness between them contains. Not emptiness, not void, not the simple absence of light in a universe that lacks an atmosphere to scatter it. You will see the message. The age of the cosmos, the expansion of space, the horizons beyond which reality continues without you, the ancient microwave glow of a universe that was once a furnace of visible light, now cooled and stretched into silence, the infrared whisper of galaxies whose light departed before the Earth existed, arriving in a language your eyes were never built to understand. The darkness is not an absence, it is a record, and the most terrifying part is not what it tells us. It is that the universe is slowly, methodically, permanently taking the rest of the story away. The pages are being carried beyond the horizon one by one. The evidence is fading. The window through which we can still read the message is narrowing with every passing eon, and when it finally closes, the darkness will be all that remains. Not because the universe ran out of light, but because it carried the light beyond the reach of anyone who might have seen it. We are here, now, in the narrow window. The message is still legible, the darkness still speaks, and for this brief, improbable moment in cosmic time, we are able to listen. Think about what that means. Not as an abstraction, not as a cosmological curiosity. Think about it personally. You exist at a specific moment in the 14 billion year history of the universe, and that moment happens to coincide with the narrow window during which the cosmos is still legible. A few billion years earlier, and the cosmic microwave background would have been too hot and too bright to separate from the foreground of newly forming galaxies. A few 100 billion years later, and it will have faded beyond recovery. The expansion will have carried the evidence away. The sky will be empty and silent and permanent in its darkness. You are here now, in the interval between too early and too late, and that interval is vanishingly small compared to the total lifespan of the universe. Consider creatures that live near hydrothermal vents at the bottom of Earth's oceans. They exist in total darkness, miles below the surface, sustained by chemical energy from volcanic fissures in the seafloor. They have never seen sunlight. They have no concept of a sky. The entire universe, as far as their biology is concerned, is a dark, warm, pressurized world of rock and water. They do not know they are missing anything. They cannot even formulate the question of what lies above the ocean's surface, because nothing in their experience hints that a surface exists. They are not wrong about their local environment. Their perception of their immediate surroundings is accurate, but their picture of reality is catastrophically incomplete, limited by the horizon their biology imposes. A civilization arising in the far future of Milkomeda will be in the same position. Their instruments will accurately describe their immediate cosmic neighborhood. One galaxy, empty space, no expansion, no beginning, no other galaxies. Their science will be internally consistent and observationally rigorous, and absolutely wrong about the nature of the universe they inhabit. They will be deep ocean creatures of cosmology, living in the dark, unaware that there was ever light to see. We are not those creatures, not yet. We live in the era when the surface is still visible, when the sunlight of cosmic evidence still reaches us, when the cosmic microwave background can still be measured, when distant galaxies can still be photographed, when the expansion rate can still be calculated, when the chemical fingerprints of primordial nucleosynthesis can still be read in ancient gas clouds. Every one of these observations is a gift of timing. Every one of them depends on the accident of arising during the brief cosmological epoch when the universe has not yet hidden its own autobiography. The darkness of the night sky is the opening line of that autobiography. It says, "I am not eternal. I had a beginning. My light has not filled every corner because I have not existed long enough for that to happen. My expansion has stretched my oldest glow into frequencies you cannot see. My horizons are real, and they are closing, and beyond them, I continue in ways you will never directly confirm." Every night, the sky delivers this message. Every dark gap between the stars carries this information, and most people walk beneath it without reading a single word, assuming the darkness is ordinary, assuming it is empty, assuming it is nothing. It is not nothing. It is everything we know about the age, the structure, the expansion, and the limits of the universe, compressed into the simplest possible observation: a dark sky. A sky that should not be dark if the old model of the cosmos were true. A sky whose darkness proves the universe has a history, a horizon, and a future in which the evidence we now treasure will be carried, page by page, into permanent silence. You are standing in the window. The light of the message is still arriving. The cosmic microwave background still glows. The distant galaxies still shine in infrared wavelengths that our instruments can capture. The expansion rate can still be measured. The paradox can still be stated, and its resolution can still be confirmed by observation. All of this is true tonight. It will not be true forever. The darkness is not the end of the story. The darkness is the story. And for now, just for now, we are still able to read it.